This video is a presentation I've been giving for years in support of producing clean energy from farm, garden, and household wastes. All the info you need, including plans and parts lists, are available in my book, DIY Biogas. Check the link in the description. We'll cover all the basics, but perhaps not all of the nuances you'll need to know in order to make and use biogas. But let's start at the beginning. Biogas is a mix of gases. The combustible part of biogas is methane, and carbon dioxide will also be produced, but CO2 doesn't burn. There are often additional gases formed as byproducts of the digestion process, and they're related to what you feed the digester. Cows are a large producer of methane gas and will play an important role in getting started in your DIY biogas project. Anaerobic digestion, which I sometimes call AD, starts with methanogens. These are single-celled, non-bacterial microorganisms from the biological group Archaea. They are required. You can find them abundantly in cow poop, pig poop, and sometimes at the bottom of a swamp, which is where, you guessed it, swamp gas gets its name. You'll need to inoculate your digester with methanogens to make methane. No methanogens, no methane gas. Biogas wants to happen. It's a natural process. When you enhance and manage those processes, you can better control the outcome. You'll want to develop a recipe for maximum production based on what you can feed your digester, then manage the gas that gets produced to meet your needs. Biogas can be used in a simple burner to cook on, or to run a modified gasoline or even a diesel engine. Each of these end uses have specific requirements for fuel purity and delivery. AD is similar to composting, but it's an anaerobic process. An anaerobic process is one that happens in the absence of oxygen. Composting happens in the presence of oxygen, so it's aerobic. Recipe development is critical for efficiency and maximum yield. While there is an optimum ratio of carbon to nitrogen, it is somewhat forgiving. Carbon, which is typically found in brown materials, is the source of energy for the methanogens. Nitrogen, which is usually found in green stuff, is used for protein development and cell building. The carbon value shown in the chart is the C in the C to N, or carbon to nitrogen ratio. This diagram shows the basics of the material processes involved. Material goes in, liquid, solids, and gases go out. There are 4 chemical processes that occur inside a digester. Hydrolysis is the enzymatic breakdown of complex proteins, carbohydrates, fats, and oils into amino acids, simple sugars, and fatty acids. Acetogenesis is basically fermentation. It happens when acid-forming bacteria oxidize the simple compounds formed during hydrolysis to create carbon dioxide, hydrogen, ammonia, and organic acids. Acetogenesis is the conversion of organic acids into acetic acid, which is what makes vinegar. Methanogenesis is the development of methane-producing microbes by combining hydrogen and CO2 produced during the acid-forming phases to create methane. In addition to methane and CO2, there will be impurities in your gas that are related to the feedstock that goes into the digester. This goes further back up the food chain to whatever was used to grow that feedstock. Some of these impurities may need to be removed or scrubbed from the gas before it gets burned, depending on the end use. How much biogas gets made depends on how much material your system can handle and how well you manage those processes. Temperature, pH, feeding rate, mixing, retention time all contribute to conversion efficiency. Here are 2 examples of gas production figures. The first example shows how much an average cow can produce each day if you could capture all of its manure. The second is an example from my 50-gallon digester project. This test was performed on an actively producing digester that I let go dormant for a couple of weeks and then restarted. When starting up a digester from scratch, it can take 5 or 10 days before combustible gas is made. In this case, the system was primed and ready to go and started producing in just a few days. And there's no reason that all of these ingredients can't be mixed. Using cow manure in conjunction with food or garden scraps is a great way to manage waste and generate biogas. Let's talk a little bit more about the process and some definitions. Feedstock consists of solids and liquids, mostly liquids. Most vegetative material and manures are 70 to 80% water. Additional water that you'll use in your digester helps to break down material and is important in the conversion process, but it adds nothing to gas production. So imagine taking your feedstock and removing all the water from it. That's called total solids. Now take that solid material and burn it. What's left are called fixed solids or ashes. What got burned in the fire is the useful food for oxidation processes. That's where the energy is. These are called volatile solids. There's a relatively small amount of useful volatile solids in feedstocks. Most of your digester volume will be taken up by water. This means that a large digester volume is required for moderate gas production. Not all volatile solids are chemically available. This means that ultimately the biogas you produce will vary based on the specific ingredients in your recipe. Having a biogas digester is like having another mouth to feed. Feed your digester a consistent diet. Try to mimic the environment in the guts of an animal. A digester can get indigestion with a change of diet, just like people can, so avoid the bellyache and maintain a steady diet. Let's take a look at a few different types of biogas digesters. Sometimes the entire system that you put together that produces biogas is called a generator, because it's more than just the digester. The digester is the part of the generator that manages the digestion process. A batch digester is simple, but it's relatively high maintenance. It's kind of a one-shot deal. You fill the lower barrel with digestible slurry, and as the gas is produced, it fills the upper inverted barrel. Once the digestion phase is done, you need to empty the barrel and start all over again. There are lots of options for building a plug flow or continuous flow digester. These are fed a periodic plug of material, and as new material is put in, effluent is pushed out. I've seen them made out of heavy-duty plastic bags and even old culverts. As long as it's airtight and you can manage your process and flows, give it a shot. This is the generator design I landed on and seems to work well for my needs. It's a hybrid continuous plug flow design. A continuous flow digester is a little bit more complicated than what I would call a plug flow digester system. The individual components need to be sized correctly, but it can be more practical to operate. This hybrid example is similar to a plug flow, but separates the digestate from the gas, allowing for more consistent and better managed flow of both digestate and gas. Here's the business side of things. It's not pretty and it smells bad. Finer material will react better, so I used a food grinder attached to an outdoor sink, which provides a pretty nice slurry when mixed with water. The digester vessel contains mostly water. In addition to the feedstock moisture content, you'll also add quite a lot more water. Be sure to leave some space in the barrel to allow for material expansion. After a week or two, combustible gas will start to be made. It's important to remember that the first gas produced will be mostly CO2 as the oxygen in the tank and material is used up. Once the vessel becomes anaerobic, there will be more methane produced. This is a simple 5-gallon batch generator connected to a Bunsen burner. It's helpful to start small so you can wrap your head around the processes, how things work, and develop your own recipes. Complete plans and a parts list are included in the DIY biogas book. The 5-gallon bucket is a great science project for your school. Because there's a lower content of methane in biogas as compared to natural gas or propane, you'll need to modify the burner for optimum flame. This usually means a larger gas orifice and less excess air. Nozzle orifice sizing guidance is also provided in the DIY biogas book. Burners are somewhat forgiving, but engines are not. If you want to run an engine on biogas, you'll probably need to scrub out the impurities. You'll want to size your gas storage system according to how much gas is produced and the rate of consumption. Storage is where you'll want to increase the pressure to what your burner needs. Please be safe. You're working with flammable gases and they can cause great harm and destruction if you don't take proper precautions. To prevent flashback, which can happen if the biogas pressure is low enough to allow the flame to move backwards through the gas line into the generator or gas storage vessel, which can be quite explosive. A simple flame arrestor can be made with bronze wool. Push an inch or two of it up into the gas feed tube, and that should be effective in preventing the flame from moving backwards through the hose. Here's another simple flame arrestor design. A few inches of water in the hose allows gas to bubble through, but prevents the flame from moving through it. This trap isolates the digester vessel from the gas collection vessel. A quick shout out to the cleancooking.org group, where good people are working towards cleaner, safer, and healthier living conditions by providing access to clean cooking fuels and methods, including biogas and wood gas cooking. All the details you need to make this happen are in the book. Thanks for watching. I hope you will like this video and subscribe, and please leave any comments or questions. Let me know if you've tried making biogas and what the results were.